Good day everyone. Throughout our control system design laboratory activities, I learned that designing a control system is not only about making a system work but also making it respond efficiently, accurately, and reliably. The experiments helped me understand how different parameters affect the behavior of a system and how engineers use these concepts to improve performance. One of the first thing I learned was the use of MATLAB, Simulink, and Simscape. These tools allowed us to model and simulate systems without having to build actual hardware. Through Simulink, I learned how block diagrams can represent real systems and how simulations help us predict system behavior before implementation. Simscape further expanded this understanding by allowing physical systems to be modeled using real-world components and connections. This showed me how important simulation tools are in engineering because they have saved both time and resources while providing accurate results. As we progressed through laboratory exercises, I gained a deeper understanding of second-order systems and their performance characteristics. I learned that system performance can generally be divided into two categories: retraction response and steady state response. A good control system should reach its desired output quickly while minimizing errors and unwanted oscillations. One of the most important concepts I learned was the effect of damping ratio on the step response of a system. Through simulations, I observed that when damping is low, the system oscillates more and experiences higher overshoot. As damping increases, the oscillations decreases and the response becomes smoother. However, too much damping can make the system slower in reaching its final value. This taught me that control system design is often a balancing act between speed and stability. Another lesson involved the damp frequency and its influence on system response. By varying the damp frequency while keeping other parameters constant, I observed that increasing the obs- damp frequency generally made the system respond faster. The system reached steady state more quickly while maintaining acceptable stability. This experiment helped me appreciate how engineers can tune system parameters to achieve desired performance specifications. The laboratory exercises also introduced us to important performance measurements such as peak time, percent overshoot, and settling time. Instead of simply observing graphs, we learned how to calculate these values mathematically and compare them with simulated results. I found it interesting that the calculated values were very close to those estimated from the graphs, proving that the theoretical formulas accurately describe system behavior. This strengthened my confidence in using mathematical analysis to predict real system performance. Another valuable topic was the effect of zeros on a control system. Through simulation, I learned that a zero located near the system poles significantly affects the transient response, often creating a more aggressive response and increasing overshoot. On the other hand, a zero placed far from the poles has a very little effect on the overall behavior. This showed me that the location of the zero is crucial when shaping system performance and achieving specific design objectives. We also studied the impact of adding additional poles to a system. I learned that extra poles generally slow down the response, increasing rise and settling times, and make the system more damped. The experiments demonstrated that poles located far from the dominant pole, such as at negative 100, have minimal influence because their effects decay quickly. However, poles near the origin, such as at negative 1, greatly affect system behavior by slowing the response and making the system more overdamped. This helped me understand the importance of pole placement in control system design. Overall, the laboratory activities taught me that control systems are not just theoretical concepts but practical tools used to ensure stability, accuracy, and efficiency in engineering applications. I learned how simulations, mathematical analysis, poles, zeros, damping ratio, and frequency all work together to determine system performance. Most importantly, I realized that successful control system design requires balancing responsiveness and stability to achieve the best possible outcome. So that's all. Thank you.